Now, if you remember the past when we were doing and talking about limits, we mentioned that we have a couple limits that we were going to take per granted without explaining properly where they're coming from. Well, let me not precisely explain now where those limits are coming from, but let me give you a glimpse of what they're really doing, or what are they representing. So we have two things that we call here into play, and it's the limit when x goes to 0 of sine of x over x. But if you think about it, this is the same that the limit when x goes to 0 of sine of x minus the sine of 0 over x minus 0. And if you remember what that is, that's pretty much the derivative of the function sine of x, so f prime at the point 0, or of course assuming f of x is sine of x, right? So we're talking about that, we're analyzing what the derivative is at 0. And it turns out that that's going to be 1. Okay? So the slope of the tangent line at x equals 0 is just going to be 1. Okay? And that's going to make sense in a little bit. But also, and then at this point, probably you cannot see where I'm going with this. The other limit has the same situation. So we had the limit when x goes to 0 of cosine of x minus cosine of 0 over x minus 0. Notice that cosine of 0 is 1, x minus 0 is x. And so again, if we assume that g of x is cosine of x, this is essentially g prime at 0. And we're saying that that's 0. So now this is talking about the tangent line of the function sine of x and the tangent line of the function cosine of x. So now let's take a look at what happens if I'm approaching with numbers. So if I do a table and I approach by the left side and the right side with point like 0.1, 0.01, and 0.001, notice that sine of x over x is going really, really close to 1. Okay? So without taking the derivative, I kind of can get my result. I can get my approximation. Yes, this is going to 1. Okay? And what's happening is this situation here in the graph of sine. So the sine of x over x, essentially what I'm saying is that when I approach, this is going to give me 1. But notice this graph over here. This is not really the graph of sine, right? Because in sine it doesn't have a 0 in here. Okay. So what's going to happen is that we can take a look at the tangent lines and then from there tell what the function is. It turns out that the tangent, the graph of sine of x over x ends up being this. And so at the point, if you take a look at the graph of sine, notice that when I'm at 0, if I get a tangent line over here, it's going to be aligned with slope 1. Okay? And this is going to be the graph of the derivative of sine, which is cosine. Okay? How do we obtain that the derivative of sine is cosine? Well, we do this process of analyzing step by step what the graph is via the tangent lines. So notice, what is the points where sine of x is 0? Well, sine of x is 0 is going to have a slope 0. So it's going to have a slope 0 at all these points. So at all the peaks, the top peaks and the bottom peaks. Okay? So what is this number? This number is pi half. This is 3 pi half. And then this is 5 pi half and so on. Okay? So in every single pi half something, we have that the slope of the tangent line is 0. So that's going to give me the zeros of this function. Okay? So with that, I'm saying, oh, okay, so it has the same zeros. And now when I'm calculating the slope of the tangent line, Notice that this is telling me, oh, the slope of the tangent line is positive here, then it changed to be negative. So we have this transition from the function being positive to being negative to having a transition in pi, because pi is a 0 of the function. Okay, and over here, this is going to be a transition point in the derivative. Now, notice that here, the slope is still negative, but then it transitions to be positive here in 3 pi half. And so we have all this behavior. And so from the graph of the sine of x, we can kind of trace how the values of the derivatives are going to be. And it turns out that when we compile not only the series of the function, but the behavior, we obtain that the derivative of sine is cosine of x. Okay? So via the analysis of the tangent line of points, we can graph the derivative of sine to a cosine. Okay? Now, a similar thing happens if we start with cosine. Notice that we can get the points where this is 0, where the peaks of the cosines are, and relate them with series of the function of the derivative. Okay? And then analyzing the behavior is the slope. Notice this slope is negative, so the function here is negative. This slope on this interval is positive, so now here this is going to be positive. And remember, each of these peaks represents a 0. So this is representing the 0, this is representing the 0, and in between the slope of the tangent line, so if I take a point here, the slope of the tangent line is going down, so that means it's a negative. It's a negative slope of the tangent line, so that means that the function is negative here. Okay? And let me show you that behavior again in the board. So if I'm gonna do that in the board, and if I have cosine, so cosine is a function that is doing this kind of behavior, well, more or less. So let's say that this is 1, right? And over here this is -1. So the height of this, okay, so a little bit skewed. Now notice the slopes are flat in here, and they're flat in here. And so according to what I'm saying, if I'm going to graph my derivative function, I'm just going to use those points to reflect now where the function is. So this is now a 0 of the derivative function, and this one here is also going to be a 0 of the derivative function. Okay, so these two correspond to zeros. And now if I'm talking about here in this place, notice that if I take a point here, the slope is positive, so that means in this part the slope is positive, right? So the function is doing something over here like this. It's in the positive. Then it reached to 0. Then now notice in all this piece, if I take a point here, or a point here, or a point here, the tangent line is going down. So that means that the slope is negative. Remember, y equals mx plus b, which is a line. M is positive, then you have something like this. M is negative, you have something like this. Okay, so in this cases we have negative slope, so that means that the f prime is negative. So, but it's crossing back in this 0, so that means it gotta be doing something like this. Okay, and so that's why we end up having back now when we're taking the cosine of x. Now we end up having the function f prime sine of x back. Okay. And so in general, we start with the derivative of sine and cosine, and from there we're going to use properties of the trigonometric functions to find out who the other derivatives are. And so we're going to have that these are all the derivative functions. So for example, the derivative of sine is cosine, the derivative of cosine is minus sine. But then now we're going to have the derivative of tangent is secant square, and the derivative of secant is secant by tangent. In the same way, the derivative of cotangent is minus cosecant square, and the derivative of cosecant is minus cosecant by cotangent of x. Now, you might be saying, oh, okay, but how do we get those results? Okay, so let's do one example of these things. So first, we're going to go with the derivative of tangent of x. Okay, first, we got to remember that we know the sine and cosine derivatives. We're going to assume that as the starting point. So we're going to transform tangent into something of sine and cosine. So tangent is sine over cosine by trigonometric identity. And so now this is the derivative of a quotient. So we got the derivative of sine times cosine minus sine of x, the derivative of cosine of x over cosine of x square. Okay. Now from here we can compute the derivative. Derivative of sine is cosine. So we're going to have cosine times cosine minus sine. And then now the derivative of cosine is minus sine. Okay. So that is according to the rules that we just established. And now this is cosine square, which I'm going to see as cosine square of x. Okay. But now if you take a look at this, this is just cosine square of x plus sine square of x. Okay. And that identity is a trigonometric basic identity. So that's going to give me 1 over cosine square of x. And so from there, we can conclude that this is secant square. So the derivative of tangent is secant square of x. Okay? And that's the way that we obtain this. So now something similar is going to pan out for us to obtain all this. Now I'm going to do cosecant of x, and I'm going to leave cotangent and secants for you as a practice. So let me just clear out the spacing here. Now let me do derivative of cosecant of x. So now the cosecant, of course, is an identity related to sine. It's 1 sine of x. So this is going to be a quotient rule again. But this is going to be one that is much more simpler. We got the derivative of 1 times sine of x minus sine of x. Sorry. Minus 1 minus 1 derivative of sine of x over sine of x squared. So thanks to that, we can simplify. The derivative of 1 is 0. So this is 0 times sine of x minus the derivative of sine of x, which is cosine, over sine. Notice this sine times 0 is going to be a 0. So we're going to get cosine of x over sine squared of x. But if we want to simplify, maybe we just need to use one of the signs. We can use we can see this as cosine divided by sine, and separating this 1 over sine. And so notice sine squared, so split at sine times sine, so we don't have any change. And now this becomes cotangent, right? Oh, I'm forgetting this minus. So minus cotangent of x, and sine again is cosecant of x. And that is the origin here for the trigonometric derivatives.